Another incredibly important thing for us to know about stars are how powerful are they? How much energy is that star giving out every second? And we can determine that by understanding more about the light of the star or the luminosity of the star. I remember hearing our author Alex Filipinko talk, and he was saying that luminosity is like the oomph of a star. Now, oomph is not a terribly scientific word, but it basically is how much power, how much energy does that star have. So it's the power or the energy that the star gives off over a period of time. The units of luminosity are watts. Yes, the same old normal watts that you use for light bulbs or microwave ovens or toasters. And that is a joule of energy per second is what a watt is equivalent to. Now here's one of the problems when you start to try and compare one star with another star. How bright they look depends a lot with distance. This is called the inverse square law, and I found this set of photos on the internet, and I think it's absolutely fabulous. Here is a woman who's being photographed, and she's at a particular exposure, and she's 1 foot away from the light source. She moves twice as far away, 2 feet away, and her light on hitting her is 1/4. So she goes down to 1/2 squared, or 1/4 the quantity of light when she's only just twice as far away. When this woman moves to 4 feet, or 4 distances from the source of light over here, the amount of light that's actually hitting her is 1/6, or 1/4 squared. So how bright something is going to appear will have to a great extent, is going to depend upon how far away it is. Another example is to say that if you had a 100-watt light bulb and you doubled the distance, it will appear to have the same brightness as a 25-watt bulb, or 1/4. Mathematically, this is the same as this situation. Double the distance, 1/2 squared, 1/4 the amount of brightness. This relationship is referred to as the inverse square law. And the inverse square law we have already talked about when we talked about gravity. Light, all different kinds of light, follow the inverse square law when we start talking about brightness and luminosity. All force fields, meaning magnetic fields, electric fields, and of course gravitational fields, also follow the inverse square law. The quick version, without going into a little math, is all of these things have a tendency to get much weaker with a small change in distance. So if I'm 1 distance away, my luminosity is going to be 1. If I change to 2 distances away, my luminosity is going to be 1/2 squared, or 1/4. Triple the distance, my luminosity is 1/3 squared, or 1/9. And you can start to see that relationship: 1/4, 1/9, 1/16, 1/25, etc., etc. When we compare stars, there are 2 different terms that are used, and they both sound very much alike. One of them is the concept of apparent magnitude. Now, apparent has kind of buried in the word apparent is the word appear. And apparent magnitude is how bright stars actually look in the sky. Now, because of this inverse square law, stars that are closer are going to look brighter than stars that are far away. But that just how you look out and how bright does it appear, that's called apparent magnitude. The apparent magnitude scale, if you remember, was invented thousands of years ago, and 0 was considered at the moment it was invented to be the brightest object you could have. Fainter stars have positive numbers, and negative objects, negative stars, things that we've discovered since then that we want to put on this magnitude scale, bright objects actually have positive numbers. So the Mars has a magnitude of -2.8. Venus, negative 4.4 with this very large albedo, very reflective. The moon has an apparent magnitude of negative 12.6 in brightness, and the sun, negative 26.8. So they actually know the brightnesses of all sorts of different things. Now, what we just talked about was apparent magnitude. How bright do things appear? What we need in order to do some good scientific research is know exactly how bright different stars absolutely are. And this is referred to as absolute magnitude. This is brightness with distance taken into account. Now, if we know how far away stars are, we can take the apparent magnitude and we can calculate absolute magnitude. But in order to do this, we need to know stellar distances. How far away are stars? And that takes us back to the triangulation method up here. And that's used by these satellites and measured with parsecs. We need all of this information in order to just determine how bright stars really, really are. That's going to do it for this time, and next time we're going to come back and talk about Hertzsprung-Russell diagrams.